Today I will introduce our paper SeaK Rethinking the Design of a Secure Allocator for OS Kernel. And our work is a joint work by Nanjing University, Boulder, Northwestern University, IBM, and Virginia Tech. And we got all 3 badges from the USENIX AE committee. And our work is implemented by eBPF. And thanks to the previous presenter's contribution in safe eBPF, our work can be implemented with a solid base. And hopefully, our work may prevent the exploit, which will be introduced by the next presenter after me. And my name is Yicheng Guang, the presenter. And let's see the summary of Linux kernel heap exploits. And there are mainly 2 taxonomies based on the initial corruption or exploit techniques. The first is spatial or temporal overlapping. And for spatial overlapping, the most common one is out of bound. And for temporal overlapping, one example is use start free. And the second is within or cross cache. And literally, within cache is to apply exploits within the same cache. And cross cache is to apply exploits across different caches. And the essence is actually the overlapping between corruptions introduced by vulnerable objects and sensitive data in victim objects. And let's see how existing Linux kernel hardenings perform. And there are 3 types. The first type is by default enabled. We call them C1. And the second type is by default disabled. We call them C2. And the third one is lightweight debugging feature. We call them C3. And this one only includes slab debug. And let's see how they performed. For C1, the hardenings in C1 are widely bypassed. And for C2, keyfans can only protect a small portion of target objects. And securely storing random seed is challenging in structure layout randomization. And for C3, C3 can prevent most exploits, but it fails when it faces the dirty cred attacks. We also did a performance test on the existing Linux kernel hardenings. As we can see, C3 has significant performance overhead. And in the left table, the performance overhead is up to 177. So C3 is used as a debugging feature by default. So our insight is that if we want small overhead, the effectiveness could be low. And if we want high effectiveness, the overhead could be unaffordable. So the trade-off between overhead and effectiveness persists if we protect every kernel object. So thinking from another perspective, do we really need to protect every object? And the answer is definitely no. So what really matters is exploit critical objects. And what is exploit critical objects? And by exploit critical objects, we mean vulnerable or victim objects. And the first paper, this paper focused on the vulnerable objects, but vulnerable objects vary from bug to bug. And this 3 paper focus on the victim objects. However, we keep finding new victim objects in the future. So the challenge is it's impossible to have an oracle set of all exploit critical objects. So our key idea is an on-demand secure allocator. The allocator has 3 features, including protection on demand, type granularity, named atomic alleviation, and dynamic enforcement. And here's an example. In the kernel, we have many subsystems, include Bluetooth or the file system. And we also have many objects, include struct stack and struct file. And if a hacker exploits the struct file, and this file is exploited, and there may be a bug in the file system, and at this time, we just protect the struct file, not protecting every object in the kernel. And the exploit will fail, and the bug will never be triggered again. And as the previous presenter just introduced the eBPF, we just simply skip this part. And for the design overview, in our design, we first have a eBPF synthesizer in the user space. And it's to synthesize an eBPF program to instrument the kernel. And we also use this program to replace the kmalloc and kfree with our own strategy. And we also have a BPF maps. This maps is to manage the metadata of dedicated regions and isolated objects. And in the dedicated region, we can isolate objects with guard pages and random offset. And here's how we can synthesize the eBPF. And we only need two kinds of input. And the first is function plus offset. It's actually the allocation side and free side, and it's where we instrument eBPF programs. And the second is KPI type. And KPI type is the type of allocate and free function in kernel. And different KPIs have different prototypes. And here's an example of KPI type. And in kernel, we have kmalloc and kmem-cache-alloc. And in our program, we need the object size to synthesize our program. And in the kmalloc, object size is the first parameter. And for kmem-cache-alloc, object size is a field of kmem-cache. So we have to apply different methods to read object size, considering different KPIs. And for runtime separation in detail, we first have two maps. The first map is region to index. And this map is to look up the dedicated region to allocate objects with IP size privilege zone as keys. And second is object to region. It's to look up metadata according to object address. And in the dedicated regions, we have guard page to prevent spatial corruption intro-dedicated region. And we also have random offset to prevent temporal corruption intro-dedicated region. And we have an example. It's actually dirty cred. And dirty cred is used after free. And the nature is temporal overlapping between objects with different privileges. And here is a struct file representing a readable file. And we free this file with a dangling pointer generated, and with an allocator struct file representing a readable and privileged file. And here is how we synthesize the eBPF. And here, from the bug report, we can see the allocation side. This is the allocation side of file object. And here is the free side of the file object. And we use the information of allocate and free side to generate the eBPF program to protect the struct file. And here's an example of key. As we can see, the third part, it represents the privilege of the object. And the struct files with different privilege will be allocated in different regions. And here's a demo. And as we can see in the left, we first open up our protection, and on the left, the exploit fails, and we then stop the protecting, and the exploit will succeed. And as we can see, it successfully gets into the root bin bash. And we also did an effectiveness evaluation. And for separating vulnerable objects, our work can successfully prevent all the exploits we select in our paper, including dirty cred. It's because we select privilege as our key. So files with different privilege will be allocated in different regions. And for separating victim objects, our work can prevent all the bugs, all 48 bugs we select in our paper. And for performance overhead, we have 4 kinds. The first is cold, and cold means scarcely allocated objects, and hot means frequently allocated objects, and durable means objects with long lifespan, and fire is just struct fire. And even for the hot type, the overhead is really small. And the negative number here is actually the fluctuation of LM bench. And for memory usage, even for 64 cases, the overhead is really small. And for scalability, even for the 64 cases, we can see the overhead is negligible. And our contribution is a secure kernel allocator protecting exploit critical objects. And it contributes the insights of inherent obstacles of designing a secure allocator. And it also proposes a new and practical strategy to secure kernel heap. And it provides open source design and implementation with negligible overhead and high scalability. And here is our GitHub repo. You can reproduce our experiments in the video I just showed. Follow the instructions on the GitHub repo. And here's the contact. You can contact me by email. And thank you. Any questions?